Hi everyone, today we're on Unit 10, Lesson 5. We will be talking about one-sided limits. We already talked about this a little bit earlier in the unit, but let's kind of review before we begin. So if we look at our do now, and we're given the graph below of f of x, we want to evaluate each limit. So in the first instance, I want to look at the limit as x approaches 0 from the left, because that's what that little negative sign means, of f of x. So I'm going to go to the graph of my function. Here's 0. If I want to know what's happening to the y values on the graph, I'm going to look at what's happening as x approaches 0 from the left. And as x approaches 0 from the left, my y values are getting closer to 0. The limit as x approaches 0 from the right. So now if I start out to the right, as I plug in numbers that get closer to 0, my y values are getting closer to 1. Remember, I don't care what I get when I plug in 0. I only care what I get when I plug in numbers that get close to 0. The limit as x approaches 0. Now I have to consider both directions. Okay. So let's say we look there and look there, right? Are my highlighted sections going to the same value? No, right? This and this are different numbers. So the limit as x approaches 0 does not exist. They have to be the same value in order for it to exist. And we did discuss the other day, when you see a jump like that in the graph, that's going to mean the limit does not exist. The limit as x approaches 3 from the left. 1, 2, 3. Maybe I'll give myself a little bit of a... So I'm looking here on my graph, right? I'm looking at 3. If I go to the left side of 3, and I consider what's happening to my y values as I plug in numbers that get closer and closer and closer, my y values are going to positive infinity. The limit as x approaches 3 from the right. My y values are going to negative infinity. Technically, okay, well, the limit as x approaches 3 of f of x, we know does not exist, because we did talk about when we do an overall limit, when we're not considering one side or the other side, our answer is does not exist. But when we're considering each side separately, we can use infinity. So that's something I'm going to mention again in just a minute, but that's what we want to remember. So over the past couple of days, we've been discussing the limit as x approaches f of x equals L, some number, that's all that means, by evaluating what we call a total limit or a general limit. That is, as x gets closer to but remains unequal to c, the y values get closer to L. Earlier in the unit, we discussed whether we are using an algebraic function or by looking at the graph, x can get closer to c in two ways, by approaching from the left or the right. So I just want to remind you, there's my c. X approaches c from the left. X approaches c from the right. My left limit, my right limit. If those two match, let's just use n this time, our limit is going to be some number. Limit as x approaches c from the left of f of x. If that equals the limit as x approaches c from the left, from the right then whatever that number is, right? Whatever that number is, if it's the same, that's your answer. That's what we have to remember. And we also want to remember when we're doing one-sided limits, we can use plus or minus infinity to describe left and right limits. But we cannot use plus or minus infinity to describe an overall limit unless they're the same. If they're both going to infinity, then you can use infinity. If they're both going to negative infinity, you can use infinity as well. But more often than not, we just use does not exist for those situations. When we're looking at the graph of a function, it's pretty easy to do. When we're dealing with algebraic expressions, sometimes students struggle. So let's just kind of move slowly through these examples. Whenever we evaluate a limit, it doesn't matter what we're being asked to do. Always start by plugging in a number. Don't worry about the positive or negative until you're in the problem. So the limit as x approaches 2 from the left. Always start by just plugging in. 2 times 2 minus 7.
Attention freshmen and sophomore teachers of the building. I will now be turning off the bells. Please use your own clocks and cell phones to determine the beginning and end of periods. I am now turning off the bells.
So to continue on with this problem, we would get 4 minus 7, which is equal to negative 3. So in this case, that positive or negative didn't really matter to us. And if you think about it, 2x minus 7 is just a line. So it's the left and the limit and the right limit are going to equal each other. So it doesn't matter. In example 2, the limit as x approaches 2 from the right of x squared minus 4 over x minus 2. Now this is a rational function, so it may matter. So we have, but again, always start by plugging in. When I plug in 2, I don't get an answer. So now because I'm just evaluating a limit, we're going to do what we would normally do. Factor, try again. This is the normal progression of these types of problems. The limit as x approaches 2 from the right of x plus 2 is going to be, now when I plug in 2, I get 4. So I got an answer. And what we know about the behavior of rational functions, this means there's a hole in the graph. So as I'm plugging in numbers, as x approaches 2, I'm not going to get an answer when I plug in 4. But if I plug in a number a tiny bit bigger than 2, my graph is going to go like that. What about less than 2? That's the example of our hole in our function. In example 3, the limit as x approaches 4 from the right. Always start like you would. Always start by plugging in the number. 4 over 4 minus 4, 4 over 0. This function value is undefined. So I want to describe what's going on in the graph if I plug in a number a little bit bigger than 4. I'm sorry. Go back up since it's undefined. We go back up to the original. This one can't factor. I can't factor and simplify it. So I know the limit is not going to exist. So now because I know the limit does not exist, now I would plug in a number a little bit bigger than 4. So for instance, so we can't factor and simplify. So I know this limit does not exist. Okay, I'm just going to start there for a minute. So when the limit does not exist, we know this, there's an asymptote. When I plug in 4, I get an asymptote. So I want to know now, when I plug in numbers a little bit less than 4 or a little bit greater than 4, which is this example here, what's happening to the graph? Is it going to positive infinity? Ugh. Or is it going to negative infinity? That's our question. So we take a number a little bit bigger than 4, and we use signs to help us. 4.1 is a positive value. 4.1 minus 4 is a positive value. So this graph is going to positive infinity. That one is the winner. While we're here, let's do the limit as x goes to 4 from the left and see what we get. So the limit as x approaches 4 from the left. Now we take a number a little bit smaller than 4, 3.9. 3.9 minus 4. Positive infinity, it's a positive number, a negative number. So this from the left, I'm going to negative infinity. Okay. So this analyzes the behavior. Okay. You're only going to do these steps right? Only if it does not exist. Only if after you factor and simplify, you don't get an answer. Okay. The limit as x approaches 3 from the left. Okay, so all we're considering is 3 from the left. Start by plugging in 3. 3 plus 3, 6 over 0, undefined. Normal progression, factor, try again. So the limit as x approaches 3 from the left does not exist. Since I get does not exist, now I do the extra step. Plug in a number a little bit less than 3. 1 over 2.9 minus 3. 1 is a positive value. In the denominator, I would get a negative answer. So my answers, when I plug in a number a little bit to the left of 3, are going down to negative infinity. Okay. Now, the real reason one-sided limits are so important in math is when we're evaluating one-sided limits, when we're dealing with piecewise functions. Because if you recall from our study of a piecewise function, it literally changes functions. So we have to see if the behavior is the same or different on either side of a value. Okay. We can do this without actually sketching the graph of the function. We can do this algebraically. Given f of x equals, so my graph is my x's are being plugged into x squared plus 1 when x is less than 0, and they're being plugged into x when x is greater than or equal to 0. And I want to find the limit as x approaches 0 from the left, the limit as x approaches 0 from the right, and then the limit as x approaches 0. Think about it. I find it easiest, and after a while, you won't make your number line anymore. But when I plug in values that are less than 0, I'm using that rule. When I'm plugging in values that are greater than 0, I'm using that rule. When I plug in 0, I'm also using that rule. Okay, that's not going to really matter for these types of questions though, because we only care about the left. We only care about a little bit less, a little bit greater, even though we plug in 0. For instance, the limit as x approaches 0 from the left. What I'm going to do is pick the rule to the left of 0, right? That's this portion of the x-axis. I'm evaluating in that function. What happens when I plug 0 in? Now you don't plug a number in less than, you actually physically evaluate the limit. So we plug in 0. And I get 1. Now what's the limit as x approaches 0 from the right? Now we're using this rule. Now to analyze the overall limit, the total limit, we compare the left number with the right number. If they're the same, that's the answer. If they're different, the limit does not exist. Let's try another. Given f of x equals x plus 1 when x is less than 2, and 5 minus x when x is greater than or equal to 2. Again, you might consider setting up a number line. That's the rule I use when I plug in numbers that are less than. That's the rule I use when I plug in numbers that are greater than. The limit as x approaches 2 from the left. Two plus 1 is 3. That's my left limit. The limit as x approaches 2 from the right. Equals 3. My answers are the same. So if you were graphing this function, right, you would have, the graph would be the same from either direction. So my overall limit is 2. It's not on here, but let's just try one more. So I'll give you a second. Our function is f of x equals 4 minus x squared if x is less than 1, 3 if x equals 1, and 2x plus 3 if x is greater than 1. And I want to evaluate the limit as x approaches 1. Notice the difference. In the above examples, we broke things apart for you. In some questions, it won't be broken apart for you and you have to understand what to do. That's why I always say to you, it's so important to know what type of function you're dealing with and what you have to do. So if I'm looking at this, the limit as x approaches 1, in my head, I'm saying, wait, at 1, my behavior is different from either side. Right? Basically, if you think about a number line, when I'm to the left, when I'm to the right, when I plug in 1, I get 3. I really don't care about that number at this point. I don't care about it because what do I care about? What happens from either direction? This is the important thing for me. So I need to set up, it's not in the problem, but in order to evaluate this, I need to evaluate the left limit and the right limit and see what I get. So my left limit I'm going to evaluate in this function. My right limit I'm going to evaluate in this function. What is 4 minus 1 squared? Well, that's 3. Two times 1 plus 3 is 5. That's my left limit. That's my right limit. Are those two numbers the same? If they're the same, that's your limit. Since they are not the same, the limit does not exist. Right? Our left limit does not equal our right limit. Again, I want to point out, we really don't care. We really don't care at this point what happens when I plug in 1. I'm worried about closer to 1. Alrighty, so that's a little bit on one-sided limits. We talked about how to do it. We reviewed how to do it graphically, and then we talked a little bit about different types of algebra questions we could see, whether or not your function is a rational function or whether your function is a piecewise function. You guys should practice evaluating one-sided limits. Please do your homework tonight, and we'll be back for more tomorrow. Thank you.